In statistics, something strange keeps happening, no matter what kind of data we start with. Heights, incomes, stock returns, website clicks, results often end up forming same familiar shape, bell curve. Even when original data is messy, even when it is skewed, and even when it is clearly not normal. But big question is, why does normal distribution appear everywhere? Answer lies in one of the most powerful ideas in statistics, Central Limit Theorem. This single theorem explains why averages behave so nicely, why confidence intervals work, why hypothesis testing is possible, and why so much of statistics relies on normal distribution. And best part, you don't need advanced math to understand it. Welcome back to Shital's Data Desk. I'm Shital, and in this video we are going to deeply understand central limit theorem, step by step with intuition, visuals and real life examples. By the end of this video, you will clearly understand what central limit theorem actually says, why it works, when it applies and when it doesn't, common misconceptions, and why it is backbone of statistics, data science and machine learning. Let's start from very beginning with very honest problem. In real world, data is messy. Income data is right skewed. Waiting times are uneven. Customer spending has extreme outliers. Website traffic jumps unpredictably. Most real data sets are not normally distributed. But then you open statistics book and suddenly everything assumes normal distribution. Means, z-scores, confidence intervals, hypothesis test. So here's the big question. If real world data is not normal, then why does statistics work so well using normal distribution? This is exact mystery that central limit theorem solves. Let's state theorem first. Central limit theorem says if you take random samples from any population and calculate mean of each sample, then as sample size becomes large, distribution of those sample means will approach normal distribution, even if original population is skewed, uneven, weird, or completely non-normal. Let that sink in for a moment. CLT is not about raw data, it is about sample means. That distinction is crucial. Now, this definition can feel abstract when you hear it for first time. So, before we go any further, let's build intuition using simple visual example. Imagine you roll fair six-sided dice. Possible outcomes are 1, 2, 3, 4, 5 and 6. This is uniform distribution, not normal. Now follow carefully. Step 1. Roll dice once. Record number. Do this many times. You will see flat distribution. Step 2. Roll dice twice. Take average. Record it. Repeat this many times. You will notice something interesting. Distribution starts forming small hump. Step 3. Roll dice 10 times. Take average. Repeat again and again. Suddenly, bell shape begin to appear. Step 4. Roll dice 30 times. Take average. Now, bell curve becomes smoother and more symmetric. Dice didn't change. Outcomes didn't change. Only one thing changed. Number of observations used to compute mean. And that's the magic of central limit theorem. Before we go deeper, there is very important misunderstanding we must clear up because this is where most people get central limit theorem wrong. CLT does not say your data becomes normal if sample size is large. That is false. CLT says distribution of sample means becomes normal. Your original data can remain ugly forever and CLT still works. This single clarification saves many people from confusion. So, why does averaging create normal distribution? Here's the intuition. When you average values, extreme highs are balanced by lows, random fluctuations cancel out, noise reduces, and stability increases. Each sample mean is influenced by many small independent factors, and when many small independent effects combine, result naturally tend towards normal distribution. This idea appears everywhere in physics, biology, economics, machine learning, and measuring errors. Normal distribution is not special, it is inevitable. Now that we understand why central limit theorem works, next natural question is how big does sample need to be? You will often hear sample size of 30 is enough. But 30 is not magic number. It is rule of thumb. If population is roughly symmetric, smaller samples may work. If population is heavily skewed, larger samples are needed. If population has extreme outliers, much larger samples are required. Direction is always same. Bigger samples lead to better normal approximation. Central limit theorem is gradual, not instant. It introduces very important concept, standard error of mean. Standard error tells us how much sample means vary from sample to sample. Formula is standard error equals to population standard deviation divided by square root of sample size. Two powerful insights come from this. First, as sample size increases, standard error decreases. And second, sample means cluster more tightly around true mean. This explains why large samples give more precise estimates. Confidence intervals shrink with more data, and more data leads to more confidence. At this point, you might be wondering, why is this theorem considered so important? Why does almost all statistics depend on it? Central limit theorem is reason modern statistics work. It enables confidence intervals, hypothesis testing, z-test, t-test, A/B testing, and regression analysis. Every time you hear we assume sampling distribution is normal, that assumption comes directly from central limit theorem. Without it, most statistical methods would fall apart. Now, let's connect central limit theorem to real life. In business, we use averages all the time. Average customer spending, A/B testing results, and revenue forecast. Behind the scene, central limit theorem is what allows us to trust those averages and build confidence intervals around them. In medicine, central limit theorem plays critical role in estimating treatment effects, evaluating drug effectiveness, and running clinical trials. When researchers compare average outcome across groups, CLT makes those comparisons statistically meaningful. In data science and analytics, CLT is everywhere. In confidence intervals, hypothesis testing, model evaluation metrics, and performance estimation. Anytime we summarize data using average and apply statistical inference, central limit theorem is doing heavy lifting. So, whenever you see averages being analyzed with normal distribution, remember, central limit theorem is working silently in the background. Let's step back and summarize everything we have learned. Central limit theorem explains why averages follow normal distribution. It applies regardless of original data shape. It works on sample means, not raw data. Larger samples improve accuracy and precision. It is foundation of modern statistics. Central limit theorem is bridge between messy reality and clean mathematical models. Once you truly understand it, statistics stops feeling magical and starts feeling logical. If you found this video helpful, please like, subscribe and share it with someone learning data or statistics. This is Sheetal's Data Desk, where we turn confusion into clarity, and I'll see you in next video. Thanks for watching.